This video is recommended for those architects who are already familiar with ARCHICAD and have some knowledge of Grasshopper as well. This tutorial provides a basic introduction to the features and functionality provided by the Grasshopper Live Connection Tool. Please visit graphisoft.com/rhino-grasshopper for further information and to download and install the free plugins. In this video, we will guide you through the process of distributing solar panel elements on a flat roof in ARCHICAD using the algorithmic capabilities of Grasshopper. Let's start with a simple sketch without opening ARCHICAD or Grasshopper. Here's a flat roof element where we would like to distribute solar or photovoltaic panels. There are various given rules to be considered when adding such solar systems to a building. Let's start the design in ARCHICAD by creating a slab. Later, we'll connect this slab with Grasshopper using the coordinates of 3 vertexes of the slabs, represented by the purple circles in the sketch. These 3 vertexes define the plane of the roof where we will add the solar panels. By connecting these vertexes, we can define a local coordinate system indicated in the sketch by the blue arrows. The vertexes with the coordinates define that area of the roof where we want to distribute the solar panels. We will refer to this area as field from now on. So here's a sketch of the field of the solar panels, defined by a local coordinate system using the vertexes of the slab. Let's switch to ARCHICAD and Grasshopper now and implement the previously sketched steps. We start in ARCHICAD and create a new slab. This represents the flat roof where we want to distribute the solar panels. We intentionally created a rectangular slab, the edges of which are not parallel with the X and Y coordinate directions in ARCHICAD. Now we can initiate the Grasshopper connection in ARCHICAD by clicking the Start Connection button on the Grasshopper palette. Please note that you need to install the free add-ons first to be able to enable this connection. For further details, please visit the graphisoft.com/archicad/rhino-grasshopper site. Let's display the ARCHICAD tab page in Grasshopper and insert an ARCHICAD point on the Grasshopper canvas. Let's activate the Set One Point in ARCHICAD option from the context menu. Please note that right after this action, we have to define the corresponding point in ARCHICAD that we want to reference from Grasshopper. The Grasshopper and Rhino applications are intentionally hidden from the screen to help designers focus on the ARCHICAD application and define a point there. Now we click the lower left corner of the ARCHICAD slab to create a reference point to the Grasshopper point component. As soon as we define the point, all applications are visible on the screen again. Let's use the scribble command in Grasshopper and enter a note regarding the point reference so that we'll be able to remember this in the future. Such text notes can also help others understand the project. This point will be the origin of the local coordinate system that will define the field of the solar panels as we explained in the sketch earlier. Let's go ahead and repeat the above steps 2 more times and add 2 more points to the canvas in Grasshopper and then reference these with the vertexes of the ARCHICAD slab element. We can update the scribble text in Grasshopper in order to remember which point component corresponds to which vertex of the slab. Please note that if you select a point parameter node in Grasshopper, the corresponding points preview in Rhino will be highlighted in green. Now we add 3 additional Grasshopper point elements and we connect these with the ARCHICAD points. This will convert the ARCHICAD points to Grasshopper coordinate data. Next, we would like to visualize the field area with the help of the rectangle 3-point component. We will provide its input parameters with the 3 points. As a next step, we will define the local coordinate system. Let's add 2 copies of the vector 2-point component to the canvas to define the 2 vectors that we indicated in blue in the sketch earlier. Then connect the relevant 2 points to each of these vector components. As a result, we have vectors that have directions and also a defined length. Let's use the unit vector component because this defines unit length for the vectors. Practically speaking, this means that we can use the direction of the vectors without their original length, defined by the points. We can create groups in Grasshopper to help the easier overview of the codes, and we can even enter unique titles for these groups. Let's return to the sketch. We already have our field in ARCHICAD and Grasshopper. The next step is to distribute solar panels on this field. We will create solar panels indicated by the color green. First, we define the silhouette or perimeter of a panel starting from the origin. Practically, this means that we will move with the height and width values of the panel towards the X and Y directions from the origin to define the top right vertex of the solar panel on our field. Once we're ready defining the panel outline in the plane of the field, we're going to rotate the panel around its x-axis, as indicated on the sketch. This will be the very first panel. Let's switch to Grasshopper and ARCHICAD to continue. We don't want to have fixed values for the panel sizes. To achieve this, we add two number sliders to the Grasshopper canvas. These will define the width and height values of the solar panels. Using these number sliders, we will be able to easily change the width and height of the solar panels. Next, we add move components to the canvas to move the origin of our local coordinate system 2 times to define the top right vertex of the solar panel in the plane of the field. First, we move the origin along the x-coordinate by the width of the panel value. Afterward, we do the same along the y direction by the height of panel value. To do this, we multiply the unit vector length by the values of the width and height sliders. We connect the result to the motion node of the move component. Now that we have the top right vertex of the panel, we add another rectangle 3-point component to the canvas. This will create the first solar panel outline in the plane defined by the field. Let's continue and rotate the solar panel around its x-coordinate axis. We add the Rotate 3D component to the canvas because this component allows us to define the necessary axis of rotation. First, we connect the origin point to the center input of the Rotate 3D component. This will define the center of rotation. Then we connect the x-vector direction to the axis input to define the axis of rotation. Let's check out the perspective view in Rhino to see the rotated outline in 3D. Next, we define the angle of rotation. First, we checkmark the angle input node on the Rotate 3D component to measure the rotation value in degrees. Then we connect a number slider to the angle input. Using this slider, we can change the angle of the solar panels on the roof. Please note that the results are instantly visible in the perspective view of Rhino. We can also create another group for the easier overview of the Grasshopper code on the canvas. Let's return to the sketch again. We already have the field and the first solar panel outline placed on our field. Now we will distribute the outline on the field using a certain distance. Let's call this distance gap, because this distance will be the gap between the solar panels. We'll start the distribution by multiplying the top right vertex of the first panel along the local x direction, as is indicated on the sketch. The distance between the vertexes must be the width plus gap value. Once the result of the first array of vertexes are ready, we are going to multiply these vertexes along the local y direction using the height and gap value. This will result in a two-dimensional matrix of vertexes. Once we have this matrix, we will connect all these vertexes with the top right vertex of the original panel, as indicated on the sketch. In other words, we'll create vectors, and we'll use these vectors to move copies of the original solar panel outline. As a result, we'll get the solar panels distributed on our field. Please note that we make the panel distribution on the field by creating a matrix of the top right vertex of the initial panel. There's a good reason why we don't perform the distribution using the entire initial panel, but rather only one of its vertexes. Later on in this video, we will tell you the reason behind this. Let's switch to Grasshopper and add a number slider to define the value of the gap between the solar panels. Now we add the gap value to the width as well as to the height value of the panels. This will provide the distance along the x and the y direction of the vertexes. Now we add the linear array component to the canvas. We will use the vertical and horizontal vertex distances for the input of the array. Let's add a scribble note to help find the appropriate top right vertex of the original solar panel. We connect this vertex to the geometry input of the linear array component. Add another number slider to define the number of panels along the x direction. And connect this to the count input node of the linear array component. When checking the view in Rhino, we may notice that we must specify the direction of the array to follow the local x-coordinate direction. To do this, we multiply the width of the panel by the unit vector value and connect the result with the direction input node of the linear array component. Now the view in Rhino displays the vertexes in the appropriate direction. Let's continue and multiply the vertexes along the y direction as well. To do this, we add another linear array component to the canvas. This time we connect the geometry output of the previous linear array component to the geometry input of the new linear array component. We create the direction input as before. We multiply the height value of the panel by the unit vector, and we connect the result to the direction input node. We add another number slider to define the number of vertexes along the local y direction. Please check out the results in Rhino. We used the top right vertex of the original solar panel for creating the vertex matrix. This enables us to immediately see how many panels we'll be able to fit on the available field. Let's continue and define all the vectors that are necessary to use when distributing the panels. These vectors were indicated by orange arrows on the sketch. We add a vector 2-point component to the canvas. We connect the top right vertex of the initial panel to the point A input node, and the geometry output of the last linear array component to the point B input node. Now we add the move component to the canvas to multiply the original solar panel using the vectors referring to the matrix of the vertexes. We connect the geometry output of the rotated panel to the geometry input of the move component, and also connect the vector output node of the previously added vector2 point component to the motion input node of the move component. Please note that the changes are instantly visible in the perspective view of Rhinoceros. The slanted solar panels are now distributed evenly on the roof. Let's continue and add the roof single plane component to the Grasshopper canvas. This is available from the ARCHICAD tab page. We connect the geometry output node of the move component to the curve input node of the roof component. The result is immediately visible in the 3D view of ARCHICAD. Let's add the roof settings component to the canvas. We define a value of 0.1 for the thickness of the panels. We also add the building material component to the canvas. We can use this to specify a custom material for the panels, and connect this to the building material input node of the roof settings component. Please note that the solar panels modeled with ARCHICAD's roof tool are intersecting with the flat roof. To resolve this, we will move all panels along the vertical z-axis. We add the move component, as well as the unit z component to the canvas. Here we can define a specific value for the vertical movement of the panels. All we need to do is insert this move component between the existing geometry nodes on the canvas. And the updated positions of the panels are instantly visible in the 3D views. Now let's test how easy it is to adjust the width and height of the solar panels using the number sliders. When using the gap slider, we cannot modify the sizes of the panels. We can only modify the distance between the panels. Please note that currently, we can add more solar panels than would fit on the given area. At the end of this tutorial video, we will make sure to create the maximum number of panels that will still be able to fit on the roof. Now let's see how to apply this Grasshopper code on an existing ARCHICAD building information model. Let's open an existing project in ARCHICAD. Here's the Graphisoft Park office building. We would like to add the solar panels created earlier to the roof of this office building. In Grasshopper, we use the Clear Values option from the context menu of the initial points. Next, we redefine the content of these points using current ARCHICAD points. Please do not forget to initiate the Grasshopper connection in ARCHICAD. Let's define the point values using the vertexes of the office building, as shown on the screen. We'll use the Set One point in ARCHICAD, as shown at the beginning of this tutorial video. After redefining the three initial vertexes using the roof of the office building, the perimeter of the roof area, as well as the solar panels, are already visible in the perspective view of Rhino. And as soon as we zoom out in ARCHICAD, we can notice that the solar panels are already visible in the 3D window of ARCHICAD as well. So please remember that all existing Grasshopper codes can be easily reused in various ARCHICAD projects. All you need to do is to re-establish the connection between the initial Grasshopper components and the desired ARCHICAD elements. The best news is that we can also freely use the number sliders to modify the size of the panels or the distance between them. The ARCHICAD project will be instantly updated based on the Grasshopper code. Let's return to the sketch. Now we want to make sure that we will create only the number of solar panels that can fit on a given field. We will check each generated vertex inside of our field. If it is inside, we generate a solar panel. If the vertex is outside of the field, we will not generate panels. This is the reason why we started to multiply only the top right vertex of the initial panel, instead of multiplying the entire panel. By multiplying the vertexes only instead of the entire panels, we can perform this check and then generate only those panels that will fit on a given area. This saves us computing time and ensures faster design updates. Let's make some room for the new components on the Grasshopper canvas. The second linear array component has those vertex points that needs to be checked to see if they'll all fit on the field. Let's add the point and curve analysis component to the canvas. Let's open the Help tab of this component. Here you can see that the output of this component may have various options. If the output is 0, then the investigated point is outside of the curve. If the output is 1, the point is located exactly on the curve. And if the output is 2, then the point is located inside the curve. Obviously, we'll need to keep only those panel vertexes that are inside the field, or those where the output of the point and curve component is 2. We connect the input of the component with the generated vertexes, as well as with the definition of the field. We can see that we have a lot of 2's for the output of the analysis, which signifies that many vertexes are within the field. Yet there are also some 0 values, which signifies that we have vertexes outside the field, as is also visible in the 3D view of Rhino. Let's add the cull pattern component to remove those unnecessary vertexes outside of the field. Now we connect the geometry output of the last array of points output into the list input. And let's also connect the relationship output of the point and curve output to the cull pattern input. The output of this component will provide only those vertexes that are inside the field area. We can make sure of the results of this operation if we hide the unnecessary components and display only the vertex points. We can use the number sliders to increase the number of solar panels. The perspective view of Rhino displays all the additional vertexes, even those that are outside of the field. However, the ARCHICAD 3D view will only display those panels that are inside the field. Finally, let's see what happens if we modify the original slab in ARCHICAD. Let's increase the area of the roof. Please note that we must use the Send Changes button of the Grasshopper palette to send these changes to Grasshopper. Soon after sending the changes, Grasshopper will generate additional solar panels for the roof. In fact, many more that will fit on the roof. Let's reduce the area of the roof in ARCHICAD. After pressing the Send Changes button, Grasshopper will remove all unnecessary panels from the roof. Please remember, the Rhino-Grasshopper ARCHICAD Live Connection Tool offers seamless bidirectional geometry transfer, as well as a way to translate basic geometrical shapes into full BIM elements while adding algorithmic editing functionality.